Watch this fire. It gets put out, the camera pans away, but when it pans back, the fire is burning again. Generative video models are often mistaken for functional world models. They aren't. They operate strictly as pixel context predictors, not as physical simulators. When an object leaves the frame, it exits the transformer's active context window. The model literally removes the object from its active memory. So, when the lens sweeps back, the system isn't recalling a saved physical state. It is hallucinating an approximation based on the most statistically likely pixel patterns for that area. Relying on pixel prediction to train embodied AI creates an unstable training ground where the laws of physics reset whenever the camera moves. Training a robot requires us to decouple the physical state of the world from the rendering of its pixels. This software failure is happening just as billions in capital are being deployed into physical robotics. OpenAI recently reconstituted its robotics division, formerly known as WorldSim, under Aditya Ramesh, signaling a push back into physical AI. Their objective is to leverage a sim-to-real pipeline, training general-purpose robots on synthetic data to bypass the bottleneck of real-world data collection. Hardware is standardizing alongside this shift. Platforms like NVIDIA's Isaac GROT and Unitree's H2+ provide the corporate and mechanical foundation for this movement. These machines have 75 degrees of freedom and require high precision, yet we are currently attempting to train them in digital environments that cannot consistently remember the state of an extinguished fire. You cannot safely train a highly articulate robot in a physics engine that routinely hallucinates. The digital training ground requires strict physical determinism. A $200 million initiative by the 3D AI company VAST offers a blueprint for this determinism. It's called Project Eden, and it builds a decoupled world model by separating math from visuals. The foundation is the evolving structured state. This bottom layer acts as the mathematical core of the environment. Unlike traditional methods that rely on computationally heavy 4D point clouds to map space, Project Eden uses compact structured data to independently track physical states, object semantics, and the exact consequences of actions. This layer is deterministic. An action taken at specific coordinates permanently alters the underlying mathematical matrix, regardless of what is being viewed by a camera. By moving memory to a purely mathematical state layer, the architecture solves the object permanence failures that plague standard transformers. But pure math is useless to a robotic agent that relies on visual sensors. The system needs a bridge between raw data and observation. That bridge is the state-to-observation interface. This plane acts as a geometric translator. It takes the absolute physical states from the bottom layer and converts them into perspective-driven geometric cues. If an agent moves, this layer dynamically adjusts, providing only the geometry required for that specific perspective. This interface strips visual bias out of the physics engine. The system no longer has to remember what an object looks like to know where it is. Once the geometry is defined, the system finally visualizes it. This is the final tier, generative neural rendering. This layer functions as the painter of the digital world. This neural network handles only aesthetic overlays, lighting, fluid dynamics, or smoke, based strictly on the geometry fed up from the lower layers. Crucially, this network is relieved of calculating physics or tracking object histories. It has no context window to maintain. Removing physical memory from the rendering process drops the computational cost from an exponential curve to a linear function. By isolating the neural network to a rendering task, Project Eden enables high-fidelity environments that scale without the proportional increase in compute weight seen in monolithic models. This efficiency allows for a level of scale that is required for modern embodied AI training. It enables multi-agent concurrency. Imagine thousands of robotic agents navigating a shared physical matrix simultaneously in real time. In traditional generative models, multiple perspectives rendering the same scene at once cause visual conflicts and state divergence. The decoupled architecture allows every agent to query the same mathematical state layer concurrently. They share a single physical reality while rendering independent viewpoints. A decoupled architecture is a structural requirement for deploying multi-agent robotic networks in shared physical spaces. This breakthrough addresses the industry's growing compute crisis. This chart shows how compute cost scales with environmental complexity. For traditional video generation, that cost follows a skyrocketing exponential curve. As environments grow and context windows expand, this curve hits a limit defined by the physical memory capacity of current data centers. Now, look at the trajectory of the decoupled world model. This linear trajectory allows for continuous, long-horizon robotic training that stays within the practical limits of data center capacity. The strategy of solving model deficiencies by expanding GPU clusters is giving way to a focus on structural efficiency. We are seeing a macro shift, the pivot from single-perspective generative art to persistent physical environments. The visual appeal of a photorealistic video generation model is not enough to meet the rigorous demands of embodied AI. Return to that extinguished fire from the opening scene. A system's validity as a world model is not measured by its pixel realism, but by its mathematical memory. The true world model is the one that knows, without ever having to look back, that the fire has already been put out.